Okay, so good afternoon, everyone. My name is Riina Ritasalo from Applied Materials, and we will now have 7 co-innovation projects to update. So we will first ask here Philip Anis from Aalto University, ChemZero. Welcome.
Thanks, Reena, for the nice introduction. Good afternoon, everyone. It is a great pleasure to be here on behalf of our ChemZero project to talk about how the ChemZero project plans aligns with the ChipZero goals and what is the achievements so far we got. And myself, Anish Philip, the project manager for this ChemZero project. And together with me on the stage, Joachim Justila. He is a postdoc and he's working with the computational side. So from the title, you can see like we are working with on the development of precursor tailored chemistries for tailored chemistries for developing new processes or like new precursors that will align with the universal goal of the sustainability. So how do we do? Here we focus on the following the green principles of chemistry, developing ALD precursors, and that could reduce the environmental impact, and also developing in new processes, and that will help for the semiconductor industry. And so that is the main idea here. And I don't need to elaborate on how resource intensive is the semiconductor industry and what is the adverse effect the semiconductor industry causes on the environment. And here, the ChemZero project, we act in a proactive way, like to reduce the impact of this semiconductor industry on the environment. And here, how we do this, we are trying to develop a new pathway for the precursor development that could minimize the impact on the environment, and also like to develop new process not only from the experimental pathway, also like we utilize the machine learning approaches so that we could reduce the time so that it will so that we can make it more innovative way. So we have the partners like Aalto University, together with Applied Materials, Volatech, and PyBond. So here, Aalto University is taking the lead role. Like we do the management and coordination. Not only that, like we also take care of the experimental side, like precursor development and process development. And this we do together with Volatech. They take the lead role in the precursor development together with Aalto University. And then also from the computational side, Aalto University take care of the computational part of the project. And applied materials like validation of the ALD process that developed in this ChemZero project. And Volatech, I have already told, like they do all the precursors, screening of the precursors, and then precursor development together with Aalto. And PyBond is mostly focusing on the dielectric materials, especially in the development of precursor development for the dielectrics and mainly for the dielectric materials. So we have the 7 work package. The first work package is the silicon precursor development. And then we have the next work package. We focus on the ALD process development using these silicon precursors that developed during this project. And in the work package 3, that is mostly focusing on the metal-based ALD. And then in work package 4, we deal with the modeling of the precursors and also the process, mostly for the ALD part. And then from work package 5 and 6, that is with applied materials and pi bond. So in work package 5, this is applied materials is testing the industrial way of industrial ALD process validation. So we also utilize our international collaboration in this project for the functioning of the project in a better way. So here are our the results. So the first work package that was mostly focusing on the silicon precursor developments. And the main achievement is like we already completed one master thesis, which was focused on the screening of the best ALD precursors, and together with Volatech. And in the beginning, we screened some of the precursors, and then we identified the best suitable candidates, and we developed these precursors in a sustainable approach. Because these precursors previously are reported, they were using carcinogenic solvents. So we were completely replacing these carcinogenic solvents with less harmful solvents like heftane for the development of these precursors. So we choose 3 precursors in the beginning. There's TDES, tris diethylaminosilane, and then tris dimethylaminosilane, and also we have bis diethylaminochlorosilane. So we were successful in developing 2 precursors, TDEAS and VDESCS. And TDEAS, we were able to even scale up the process, like we scale up more than 100 grams already. So it is quite, we are able to produce this in large quantities that is required for the semiconductor industry. So there is a, for just show an NMR results showing the successful synthesis of this precursor. And the second precursors we were working on is VDEACS. So this is also like we were able to develop these precursors in a small quantity, but now we are focusing on the scale up of these precursors. Also, we were able to show like we could utilize these precursors for thermal ALD of silicon dioxide. So one of the main thing of these precursors, they were not previously utilized much in the ALD of silicon-based thin films. For TDAS, there is only one report that is on silicon carbides. So there is no other previous reports, and also these precursors are not readily available in the market. And one of the advantage of these TDAs as compared to other available silicon precursors is these precursors are highly stable, and we were able to do our ALD in the ambient conditions. I mean, like we were handling the precursors in the ambient conditions. They were highly stable and minimal wastage that we observed. That means like we were able to continuously use this precursor, and even after multiple runs, ALD runs, this precursor was remain highly stable. As you can see the NMR, the before and after the ALD, there is no change in the precursor. So in a way, like these precursors are like highly useful from the ALD point of view or from the semiconductor industry point of view. So another important achievements that this project already developed is the development of silicon iodide. We know that we waste several hundred thousands of silicon wafers like every time. So how to recycle this silicon wafer? That is very important. So here in this innovative approach, we were able to develop, we were able to utilize this silicon wafer to develop a new, not new, silicon precursor, silicon iodide. So, and these precursors, like we were even synthesized in more than 10 gram. And also like the silicon iodide precursor, we were tested for ALD. But the main idea is like because everybody is aiming for lower dielectric materials, and so where we could develop the silicon oxycarbides, and how much like so other precursors are not that easy to treat with organics. So we are aiming for ALD, MLD, atomic layer, molecular layer deposition using this silicon iodide to develop some low dielectric materials. TDAs, using the TDAs, we optimized thermal silicon dioxide ALD using ozone as the co-reactant. So we were able to deposit these films between the deposition temperature of 150 to 375. And we were able to get quite pure silicon dioxide. Why I say like quite pure, like there is also some hydroxyl groups. And the growth rate is like 0.4 Armstrong. We observed like the growth rate is increasing with the increase of the deposition temperature. And the lowest temperature, 150, we got a growth rate of around 0.09 Armstrong. And all the properties were matching well with the silicon dioxide. The refractory index was coming around 1.46. And these films quite comparatively smoother. Another goal of the project was the metallic ALD. So as part of this project, we were able to develop new process for the platinum-based metallic films as a, like using titanium dioxide superlattice structures. And so here we can go from insulated to conductors. So changing the ratio of both platinum and titanium dioxide. Now we are also aiming this process like we are aiming to study the conductivity of these platinum-based thin films in high aspect ratio structures using the pillar hull chips. That process, that project is ongoing. So now I will hand over the mic to my colleague.
You can hand over this one. All right, thank you, Anish. And in addition to these experiments that were just presented and many more, we are also developing workflows to train and apply machine learning potentials to then simulate and learn more about the chemical reactivity in these processes in that way. So what we're doing is, oh, that's not the one. So what we're doing is we're leveraging these already pre-trained machine learning models, these foundational models that are trained on large parts of the periodic table, and it can be used out of the box and is stable already. So we use this to sample these reactions, and then by monitoring the uncertainty or disagreement between different models on the forces, we can then add these uncertain frames to the retraining and retrain the models, and thus improve this in an active learning scheme. So, and since we're doing this dynamically, we are no longer limited by our imagination in terms of determining reaction pathways, as these emerge as a natural side effect of our simulations. So what this enables is more realistic ALD models. And so this, compared to traditional methods such as DFT, this reduces the wall time from days to minutes, generally speaking, which means that we can spend more time on looking at the chemistry, on trying to develop precursors that are suitable for given materials, than waiting for computations to finish. And also as a side effect of these simulations, we get these 3D reaction topographies or free energy profiles, which we can then use to compare different reaction pathways. And we are also working on looking at the effects of different precursors on the deposited material. So for instance, we have preliminary experiments on these lithium precursors where we see that one of these, which is the lower one, it results in a slightly different material than the other ones. So the question of why this is, we're simulating this with this methodology to then try to learn what it is about these precursors that leads to a different type of material. So in this aspect, we're also looking at using realistic surface models. So we're using something that's, well, it's amorphous as the real substrate is, and we're looking at it with these clusters, which are also, well, more realistic than just putting the monomers into these models. Okay, so here are the current results from this project. So there are some publications that have been already published, and then there are some under review, and we also have some theses that are ongoing and finished in this project, and work that is also not shown here. So with that, I would like to thank you for your attention and urge you to ask any questions that you might have to Anish or myself. Thank you.
Okay, no questions. All right, thank you.
The TDAs you're asking? Yeah, TDAs we were able to synthesize more than 100 grams, so almost like 150, something like that, we already synthesized. Yeah, because the bulk scale, the scaling up is done by Volatech. So Volatech is taking the lead role in this precursor development. So, and yes, they have the facility, they can do, because they are in the market, precursor development and precursor synthesis are in the market. So, yeah, it is possible to synthesize it in a more bulkier quantity, yes. Yeah, there is.
Okay, short question then.
Yes. So the method I'm using is trained on DFT. So it's trained on selected DFT data. So it's a machine learning potential that is done. So it's several orders of magnitude faster to run. So you can do dynamics, and you can do dynamics of large systems that involve multiple precursors at a time, not only single precursors. So you can actually simulate layer by layer growth using this method.
Okay, maybe we need to go to the next one. So, Mona. So, Arnold Mona from VTT.
Okay. All right. Thanks, and thanks for all being here. And the next 11 minutes, I will run you through some points of circularity in semiconductor manufacturing. The long title of the project I have the honor to be the project manager of here at VTT, and which deals with the increasing the circularity in semiconductor fabrication. This project has been going on now for almost 2 years. We are approaching the end of it. We had our aim to develop new strategies and solutions for material recovery, recycling, and industrial reuse. Quite a new segment in when you discuss sustainability in this sector. We had our focus on, due to the interest partly of our industrial members, participants, on high value and critical materials, and also on water management, focusing on the recycling of CMP sludge and noble metals in ALD processes. We have been running sustainability analysis of current and developed processes, and currently working on the sustainability roadmap for the Finnish industry. There you see the project partners, both from the semicon industry and also water and waste management companies. So it's a nice mix. So I start here with, this is the classic circle of processes and the value chain in circular economy. And here our project were focusing on the raw materials and the production phase, where we look at recycling, recovery, reuse. Generally, this industry is quite fragmented. We're talking about global value chains, and there is not, we cannot really see a clear strategy that would stretch from the raw materials to the end of life of products. Saying that, there is a lot that can be done, and already a lot is being done. First, if you're looking at the design phase, which is said to define 80% of the footprint of a product, we have substitution strategies, we just heard about them, some of them, and then strategies for sustainable life cycle. For instance, adding disassembly features that will then enable the remanufacturing and reuse after easy disassembly. There is a big potential here that is actually maybe not really realized. If you look at the service life of most components, such as chips, are more than 500,000 hours, whereby the electronic products are discarded after running averagely 40,000 hours. So there is bit there. Economy of scale, you can of course ask for, looking at the fact that due to statutory background, the e-waste collection rate in EU now is already quite high. We're looking at 46%, so there is things to work with. And also the recycling business in e-waste foresee a strong growth. The industry is growing both quantitatively but also in qualitative means. When you look at the development of going towards smaller nodes, at the same time the energy consumption increases. So here we see, as an example, the energy consumption and greenhouse gas emission per wafer for CMOS fabrication. The same pattern you can see with the water consumption, as high number of CMP and wet steps leads to an increase of the ultra-pure water consumption. I did put a question mark at the water footprint though, because this can be counteracted with water recycling and reuse, which is being applied now increasingly, especially in regions with scarce water availability. Some of the results from our project, we're looking at here we have the CMP sludge, which is well motivated to work on mitigating at the same time wastewater discharge, and it's also hedging against supply risk and price volatility of ceria. Our LCA analysis has shown that by recycling we achieve a clear impact on the overall process footprint. So we have developed here new processes for the recycling of ceria particles in CMP sludge. VTT has developed a method to purify and recycle the particles in slurry after the polishing process. And here you have see some of the microscopic pictures of before treatment when they are all clumped together, and after where they are sort of like free and back to in nanoparticles and ready to reuse. Also, our partner Sophie Filtration has developed filtration-based processes for recycling. So, when you recovering recycled used materials in the semicon fab, where can you reuse it? We're talking about rather small amounts, but high quality, quite pure, and most of them critical. On the average, the semicon fab don't have a clear insight in where their sludges, metal-containing sludges go. They go away to a third-party recycler who refines them, do this and that, then to a broker, and then back to reuse somewhere. At its best, it can be used internally, but requires usually refinement by a third party. But then we see, for instance, we have seen examples of recycling into optical industry with maybe lower quality criteria in glass polishing. It can be some of the nanometals can be used as catalyst substrate or cathode material for batteries, or catalytic materials for wastewater treatment. There we have titanium oxide, for instance. They can be used in jewelry for 3D metal printing. There were maybe not in bulk, but in for instance, artisanal 3D printing. And also nanometals have seen to increase the performance of recycled asphalt and glass fibers. And lastly, in smart printing technologies in functional inks. So the possibilities are there. I've been talking much about sustainability, but I also want to point out that in addition, recycling of materials is hedging against the high price volatility of precursors and metals. And here you see, as I took as an example, gallium and germanium, two metals that are in increasing demand. Gallium in semiconductors, solar cells, and LED technologies, and germanium basically mostly in fiber optic infrastructure rollouts and solar arrays and quantum research. There is a limited supply due to the fact that these metals are produced in as byproducts in zinc production, which limits the speed with which the production can respond to price peaks. And China dominates the production. 80% for gallium and 82% of germanium are all produced in China. And due to then what China decides about exporting or not exporting, the prices go up or down. I made some interviews with some European actors about the material recovery, and clearly these last 2-3 years there's been a growing interest in recovery, and thereby also we see already some commercial projects on high value metal recovery. Here we have, for instance, from the burn wet gas abatement, where tungsten, titanium oxide, and germanium oxide has been recovered from the scrubber with ultrafiltration. We also have seen an example of lithium tantalate recovered with microfiltration from wet back grinding. Here we have by back flushing, or sputtering devices where you have high value metals from the blast glancine, inclinicine, and sheets. Silver, gold, palladium, and so on can be extracted and recovered. So next we have our sustainability roadmap, which is we are working on, and we foresee to publish that in the end of April, identifying opportunities and challenges within the industry relating to its environmental impacts, and how to turn these challenges into global opportunities. And finally, I want to market, we are running a seminar and workshop at VTT Micronova. The address is Tieto 3 in Espoo, here in Otaniemi, on sustainable RDI. So please save the date. I hope if you are interested, 23rd of April afternoon, you want to receive an invitation, please come up to me or send me a mail. Here you see my address, and thank you very much.
Any questions? Okay, thank you, Mona. the next one. ChipZero, Tuomas Pensala from VDT.
Okay, good afternoon everyone. I will present the project ChipZero, review the goals. Goals are to develop new material technology for MEMS timing devices to bring into a part per trillion stability, demonstrate the technologies in the devices and systems, system level, and then apply the system level into applications, taking benefit of the high performance timing. Meanwhile, building also an ecosystem of Finnish timing system developers and those who make use of it. The consortium forms a value chain from materials and processes via components and manufacturing to the timing devices and the applications using the advanced timing systems. We have 5 work packages. One is for substrates, developing and optimizing the special substrates that are needed by the devices. Then second is developing single crystal piezo materials for the MEMS timing devices. Third one is about polycrystalline materials. Fourth is developing gigahertz native frequency timing resonators. And fifth is demonstrators. Introduction to work package 1 on the substrates. What is parasitic surface conduction? So in the silicon dioxide covered high resistivity silicon wafer, in the interface of the oxide and the silicon, even though the silicon is very high resistivity, a charge is accumulated. And from a device point of high frequency device point of view, that looks like a parasitic conducting layer with nonlinear characteristics on the silicon, and that creates resistive losses and maybe more importantly harmonic generation, like second harmonic signal. So understanding and controlling this phenomenon is of utmost importance in gigahertz range devices. And there's 2 goals here. One is to be able to measure the harmonic distortion effects directly from wafer without manufacturing devices and characterizing them. And then the second one is modeling the fundamental origin and characteristics of the phenomenon so that the device performance can be predicted. First, let's look at what Aalto has been developing on the characterization part. So their goal is to measure directly from the wafer, not touching it in any way, the harmonic generation properties. Traditionally, it's done by fabricating RF devices like coplanar waveguide structures on the wafer, measuring them and then extracting from the results the harmonic generation properties. That's indirect and doesn't make difference what the origin of the harmonic signal is, and of course destroys the wafer as such. So is it possible to make a non-contact mapping of the wafer properties for process wafers and have this characterized kind of as an inline measurement? So here's an example of the Aalto developed measurements, a mapping of the second harmonic generation property of the wafer, non-contact with high spatial resolution, and it is successful. Takes only minutes to measure per wafer, and extracting this kind of data with the horizontal resolution by the traditional test structure would be extremely tedious, if not impossible. A test campaign has been carried out with a large variety of different wafers with the different characteristics, comparing the coplanar waveguide test structure results and the non-contact mapping, and they seem to correlate very well. And now work continues to understand the accuracy and the error limits of the measurement method. Then we move to the modeling part developed by University of Turku. So their goal is to starting from the atomic level phenomena to simulate from up to millimeter range the device level functionality. How does this parasitic surface conductivity originate, and how will it play a role in the device? The ultimate goal would be to have a model that really from the atomic properties goes up to the device level performance. It's very challenging, but the atomic level simulations have been carried out by various tools, and then they are propagated to studying a transmission line on a layered structure of oxide and silicon, and studying the electric field RF signal effect on the charges at the interface, and then leading to losses and signal the harmonic generation. It's a challenging path from the atomic scale to the device scale, but there's significant progress. So first of all, the silicon oxidization has been modeled by Turku, and in different conditions, and it's been found out that the charge formation is mainly from the dangling bonds, and extensive work has been done on the electron electric field interaction there, and it's very computationally heavy simulation, so an efficient circuit model for this behavior has been developed. And the initial results show that the biggest second harmonic signal generation comes from the the signal-induced electron distribution on the wafer, and mainly so in the horizontal, the wafer plane direction. The resistive losses and the high fields have a smaller impact on the harmonic generation. Then we move to work package 2 on the single crystal aluminum nitride-based piezo MEMS resonators. So our goal is to demonstrate the benefits of using single crystalline aluminum nitride in piezo MEMS. As test vehicles, we use SOI and cavity SOI based resonators with the 111 oriented silicon layer, which is required by the epitactic growth of aluminum nitride, and make simple resonators of the length extensional and square extensional type. The cross section is schematically shown there, the green layer being the epitactic aluminum nitride. So we have, using the Aalto tool in Micronova, have developed an MOVP process for depositing aluminum nitride up to 400 nanometers in thickness on the cavity SOI wafers, and then it produces very smooth and crackless aluminum nitride film. The XRD working core width is 0.44 degrees, which is significantly smaller than in the sputtered films. First resonators have been fabricated, epitactic aluminum nitride on cavity SOI, Q value around 10,000 at 30 megahertz, nothing spectacular as such, but it's a completely new way of manufacturing the devices. And now we have a second round ongoing with comparable resonators using sputtered aluminum nitride, epitactic aluminum nitride, and a combination of those two, so we can really compare them. In the work package 3 on the polycrystalline materials, we are studying amorphous metals with tailored properties. We have collaborated with the VTT Propertune simulation group to predict copper alloyed or doped tungsten properties, and aiming to find a combination of high acoustic impedance, low electrical resistance, and low viscous losses material. And we have done some first experiments on sputtering that yields a nice smooth film, but there is discrepancy still with the predicted and observed resistivity, but the work continues. We've also started, based on some simulation results, test on depositing molybdenum aluminum nitride by co-sputtering. There's no results yet to share about that. Then in the polycrystalline materials work package, we are also working on etching. It's atomic layer etching ALE of aluminum nitride, where the goal is to develop very extremely well-controlled etching method, like a kind of a digital etching method for aluminum nitride. And we have established that in a dry etch tool at VTT, where we can do an etch depth of 0.8 angstroms per cycle, and the cycle time being 14 seconds at the moment. The uniformity of the etch over the wafer is better than 1%, so it's similar to ALD deposition uniformity. And there's some 60 nanometer etched recesses, the VTT logo. They're using the standard photoresist as mask. Then going to the work package 4 gigahertz resonators for timing. So there's a demand for resonators with the native or the fundamental frequency at the gigahertz range out there, and we have designed 2 different variants to this need. One is a first order temperature compensated FBAR using good old silicon dioxide based compensation, but we have come up with the design that maintains very high coupling coefficient while being first order temperature compensated. So we have a K-squared of 5.5% expected from these devices. And then we have another more aggressive design, a suspended membrane type of aluminum nitride resonator, which is aiming at extremely high Q value, and where we expect to be able to demonstrate a phenomenon called dissipation dilution that can boost the Q value maybe even with decades. And this technology is also applicable, scalable to well over 10 gigahertz technology. Unfortunately, due to the delays related to the wafer size change at Micronova, we haven't been able to yet start the fabrication, but finally this month we should be kicked off with the fabrication and expect wafers to be in testing by summer. Demonstrators work package 5, no activity yet, so thank you, and happy to answer any questions if I can. It's lab scale hardware, and I can contact you with make contact with you and the other group if you would like to ask for more details. Yeah, catch me here later. Yeah. Thanks.
Could you show again this atomic layer etching?
Oh. Yes.
Because it was aluminum nitride, so just. Okay, I will contact you.
Okay. Good.
Okay, thanks, Tuomas, and let's go to the next one. So Cyril Sellet and Laura Sokka from Syke.
Eli tästä menee eteenpäin. Joo. Ehkä mä tälleen oikeakätisen pidän tän näin päin. Okay, so thank you everyone for being here, and great to have this chance to talk to you about this project. So my name is Laura Sokka. I work in the Finnish Environment Institute, which is, just in case someone of you doesn't know, it's a government-owned research and development institute, and we work in very widely in different fields of environmental protection, and we are situated. We are below the Finnish Ministry of Environment and Ministry of Agriculture and Forestry, and then VTT is also part of this project, and Minna Räikkönen from VTT is leading their part. And in this project we are studying how to enhance the sustainable circular economy of electronic devices, particularly small-scale electronics focusing on the smart devices. And we are particularly looking at the reuse, repair, and recycling options. And we have been studying this through the case study of smartphone. And this is a co-research project, and it started in the beginning of October 2024. So we are now almost, we have now had, I think, 1 year and 4 months approximately. And the project is coordinated by us in the Finnish Environment Institute, so by me. And here are the research partners, and then the funding companies that we have, so Kuusakoski Recycling and DNA, and then Certy and Rexer, who are these producer responsibility organizations, and then this is connected to Veturi ecosystems. So this where we are now, this and then also to the Spirit ecosystem. Yeah, and the aims of the project here very briefly. So we are, through this case study of mobile phones, we are studying how to enhance the sustainable circular economy of these small-scale smart electronic devices. And we are particularly looking at Finland, of course, and studying these solutions from these different viewpoints. So from the environmental, economic, technical, and then also the regulatory and the security, data security and safety related points. And one important part in this is to study the alternatives to extend the life cycle of these electronics and identify the related limitations and opportunities. And the waste and material losses are one focus here, and particularly the challenges of plastics recyclability and this untapped potential of old unused devices that are often left at home. And here are some examples of the ongoing work. So we have been doing like value chain analysis and studying the key actors for smartphone reuse and recycling. And I will talk a bit more on this later in this presentation. And we also had a conference paper and presentation in last summer in this plate conference in Denmark. And then we have had this podcast series that was ordered and that has been ordered and sponsored by DNA, so the 23 Extra. It's part of the Heikelä and Koskelo podcast that maybe some of you know. Tuntuu, että mulla on kyllä kova ääni muutenkin, että tässä varmaan meni tää. Eikö niin? Eturivillä siellä, joo. Mä nyt oon aika kaivottaja, että se luultavasti ihan hyvin saattaisi kuulua taaksekin. And and in this podcast series there have been 5 episodes by our researchers so far, and I've been very happy to give you the link if somebody is interested. But in these, particularly the potential for reusing mobile phones, which is in the interests of DNA, is discussed, and the different aspects related to that. Then there's policy analysis being done, and looking at the regulatory barriers of the present system, and here also a lot on focusing on the reuse and the lengthening of the life cycle. And then VTT has been doing the material flow analysis model for smartphones, and this I will also speak a bit more later. And based on this, also conference presentation and an article has been made, and a research visit also. And then there are these aspects of data security and cyber security, and here the cyber security barriers that are related to this circulating personal devices, reuse of them, and here especially with respect to the operating system updates and factory resetting, and and also scenarios are built on this. is he bringing another one to me? But no, it was for you. Sorry for stopping. Yes, and here some more on our ongoing work. So economic models are being built for assessing the cost implications of these different smartphone service lifespans, and consumer-driven approach and phone-focused approach is being used here. And based on this, also a scientific paper is made to this conference that will be held in Italy. And then the economic benefits of smartphone recycling are also being studied, and on this as well, a scientific conference paper has been made, and a research visit to this SUPSI in Switzerland. And then we are looking in Syke, we are looking at the assessment of the environmental benefits and impacts of the different circular economy solutions. And for this, a system level LCA, which will be integrated with the material flow analysis, and then kind of a product level LCA life cycle assessment where we are studying the lifetime extension, so either lengthening the use by one user, or then the reuse by other consumers is being studied. And for this, actually, a session proposal, including a presentation, has been made to the CETAC Europe LCA symposium, and also for this already one research visit has been made, and another one is being planned to the University of Alaska Fairbanks in actually there it says April, but May is now more likely. And then I just we have a lot of work going on, so we decided, as last year we kind of gave an overview of everything that was planned, that we now here present just a couple of results of what has already been done, or what is almost ready. So this first one is on the development and mapping of the value chains and the actors for the reuse and recycling of small-scale electronics. And here we were particularly looking at what are the potential barriers to this, and which actors are kind of play the key role in this. And like many of you probably also know, that there is a big business potentially in the global market for the used smartphones, but still particularly in Finland, the market is quite small and kind of underdeveloped. So here we interviewed 9 relevant actors that are working in the field of smartphone reuse, and like I said, the focus was in the flows of second-hand smartphones and these barriers and enablers. And here you can see the type of organizations or representatives that were interviewed. And there we have kind of built this system overview of how the phones go, and what are the different, what is happening in Finland and what abroad, and so on. But these value networks and flows are very diverse and dispersed, and typically used phones are collected at specific collection sites or electronic retails, mobile telecommunications companies, and private service providers. But many usable devices are discarded due to being locked, and this is raised up quite a lot by the companies who are taking this. And and then if it's possible to put them on, then there's the preparation for reuse, including the erasing data, functionality check, and repairing those eventually broken parts. And the private service providers usually sell the phones onwards, either domestically or abroad, but a lot of the phones collected in Finland go abroad. And here it's just some conclusions on this. So the technical characteristics of the phones, particularly the high quality phones, as well as those that have long-lasting barriers, they would be crucial enablers for this reuse. And also when there are large quantities of devices, the similar devices in good condition, it becomes more feasible to assess and prepare them for reuse, and thereby enabling this standardized operations and economies of scale. And yeah, and very important partners are those who provide the secure erasing software or services. And there are then some main technical barriers. So the limited time frame for software updates, and then these data encryption applications that prevent the reuse of phones. But one major hindrance is also the consumer behavior and attitudes. So many of us are keeping their used phones because there's maybe the lack of trust and fears of spreading data of the phones. And this is one reason contributing to this next one, but of course also that we just are a small country, so it's difficult to achieve economies of scale in small markets like Finland. And yeah, and here it's the wholesale traders that are operating in this Nordic and European markets, so globally they have a key role in this. And yeah, and more research is of course needed, but we are now in the next phase interviewing those particularly companies that are using the second-hand phones, and also those companies that are providing phones for that purpose. Yeah, and then just very quickly on this other that we had here. So this has been done is being done in VTT, the material flow analysis of smartphones in Finland. And there the aim has been to quantify the stocks and flows of smartphones in Finland, and to assess the impacts of potential circular strategies. And there is this material flow analysis being used, so it tracks how products enter, accumulate, and then on the other hand leave the system over time. And this is primarily studied as unit-based, so and the material mass of the phones are converted to the materials that there are, and composition data at the recycling and recovery phase is used there. And there are some sources of where this data comes from, and here also the partners we have in the project have been really crucial. And here are just some these scenarios that will be made. They are not ready yet, but here are some baseline results. These are for the 2024. So the annual inflow is 2.1 million phones, and kind of the active stock that is being at use is 6.9 million based on our estimations, and then again the end of life outflow is about 2.3, but it's estimated that the hoarded stock that people kind of have, that it's 11.6 million phones. And there is then the collection rate and the reuse rate, and yeah, and the average 3-year lifespan that has been applied now here is 3 years, but it could even be actually a bit lower at the moment. And yeah, and there are, I already mentioned some of these challenges, but the consumer hoarding and then the data privacy concerns, and there are also kind of limited incentives for the collection, and then on the other hand these technical barriers to reuse. And yeah, and of course these are rough estimates in that there are some data gaps and tracking problems in this, but this definitely is already giving kind of the correct amount approximately still. And yeah, and there are also some conclusions, and we have recognized that a holistic approach is here needed, so kind of combining behavioral change, improved collection systems, and technical solutions. Those could significantly boost the reuse and recycling rate. And then here, as of course always, some phones they don't go to reuse, but rather of course to recycling. And here are then already estimates of the material amounts that there are presently in these. So this can be quite, even in Finland, fairly significant sources of the raw materials. Yes, and there are the researchers that we have involved in the project, and our email addresses. So feel free to be in touch. Okay, thank you. This was all that I was going to say.
any questions to Laura?
Yes, for Finland. Yeah. Yeah, they exactly. Yeah, but it does make sense, I think, since also personally have had quite many phones at home, and as also children have phones quite commonly. Yeah.
Anything more? Okay, Mona.
I think Mona has. Uh, yeah, you mean the total use? No, no, I don't have an estimation. I mean, in VTT they might actually already have, but we haven't calculated it now. But of course, it is small amounts compared to the overall use. Of course, I assume. You mean these numbers now? Yeah, yeah. These are from the amount of waste coming to the waste treatment in a year. Uh, yeah, yeah. I think these are the recovered ones. From what I've understood, the recovery rates are fairly large then when the phones actually enter the recycling. So it is fairly efficient once they are there. But the problem is rather that they don't necessarily go there.
Okay, thank you, Laura, and we go to the next one. Ultra green. Can you maybe introduce yourself and
Hi, my name is Priya Singh Bhagar, and I'm a postdoctoral researcher in Edris Personnel Research Group from Aalto University. The topic of our presentation is Unleashing the Potential of Hybrid Energy Storage Systems in Green Energy Empowerment. Now, what is a hybrid energy storage system? A HES, it consists of power electronic devices. It also consists of battery energy storage system. It consists of batteries and supercapacitors. So a HES is actually a combination of storage elements and power electronic devices. Now, why HES is important? As we can see from here that uh, Finland has an aim of achieving carbon neutrality by 2035. It aims to have 700,000 electric vehicle on the Finnish roads by 2030. But all of these objectives, they also comes with some technical challenges. The first challenge is the low inertia in the system. It's because of the high penetration of power electronic devices that are power electronic based generators in the whole system. It is because of which there are large frequency deviations in the power grid and leads to the low inertia. The second is the unplanned charging pattern of the electric vehicle, which leads to the high power demands at certain duration, and that also leads to voltage deviations, leading to stability issues. So what is the solution? The solution is HES, that consists of batteries, that consist of supercapacitor. Now, what is the importance of these storage elements? A lithium-ion battery is the primary source. It is useful to provide a continuous and a steady power to the system. Now, why supercapacitor is important? There are certain durations in which there is high power demand for a very small duration of time. For feeding those dynamic loads, it is important to have a storage element which has high power density. Batteries have high energy density, so a combination of these two storage elements fulfill our demands. Now, how to charge a supercapacitor in the system? Lithium-ion batteries in the conventional HESS system, they used to charge the supercapacitor by using multiple power conversion stages, leading to more losses and the dip in the efficiency. So what we proposed is, in the project, a DC-DC converter stage in the middle. So this DC-DC converter is connected between the lithium-ion battery and the supercapacitor. This is a very important part of the project. This converter, actually a DC-DC converter. Now, we will discuss about the importance of this direct charging approach from lithium-ion battery to the supercapacitor in the coming slides. This is the work plan. The project coordination and management is being taken care by Aalto University. The specifications and the requirement of the HESS module are being designed by VTT. The HESS module development and testing would be taken care by ABB, Sandrex, Vansum, AU. And then the HESS module will be connected to the grid, and the design part and the control management tools will be taken care by Tampere University and Denfos. The marketing, business model, and standardization framework by Volue, Vansum, ABB, Denfos, and Sandrex. Now, what is a basic architecture of hybrid energy storage system? As we can see from the slide, there is a battery. So battery serves as the primary energy source. The supercapacitor is suitable for handling rapid power fluctuations, as we have discussed previously. That supercapacitor provides that transient power demands. It fulfills the transient power demands. The EMS connected in between is a very important part of the whole hybrid energy storage system. Now, why this EMS is important? This EMS is actually the superior control that the whole unit has. The EMS controls all the three DC-DC converters that are connecting the battery and the supercapacitor with the DC bus. So it gives signal converter 1, converter 2, and converter 3. These three signals are the output of the EMS, but the EMS decides all of these signals by considering the load conditions and the actual condition and the actual battery energy and supercapacitor. So all of these conditions are analyzed, and these signals which are converter 1, 2, and 3 are generated. So there are two types of control that are important in the whole system. The first one is a supervisory control, which is EMS. The converter has its own control system as well. So that will be discussed in the coming slides. So we were talking about DC-DC converters in the previous slide. So this is a basic DC-DC converter stage that is used to connect all the three converter stages. So this is a basic dual active bridge converter. Now, why we have selected dual active bridge converter over the other converters? There are multiple reasons. The first reason is it provides galvanic isolation between the source and the load side. It has high voltage gain, so we can change the turns ratio of the transformer and achieve the desired input voltage and output voltage. Also, this DC-DC converter can achieve soft switching, so we can even improve the efficiency. So the DC-DC converter stage here has two full bridges. The first one is the primary bridge, which is on the primary side of the transformer. The second side is the secondary bridge on the secondary side of the transformer. The input is connected, and the input is denoted as V input. Output is denoted by V naught, and the transformer has turns ratio of n:1. Now, if we talk about the different voltage stages in the HESS system, the battery voltage, the battery is connected to the DC bus. So the battery is connected to the DC bus, and the converter stage would behave as a step-up converter. If we talk about battery to supercapacitor charging, it should behave as a step-down converter. And when we use the same converter as a third unit from supercapacitor to DC bus, it should behave as a step-up converter. So this converter is suitable for all the three conditions. So this is the basic control architecture that every converter has. In the previous slide, I discussed about the supervisory control, which is being taken care by EMS. This is the control that every converter has. So there is a outer voltage loop and then an inner current loop. So the outer voltage loop has voltage controller. The inner control loop is actually a feed-forward control loop. So it has an input as V input, output voltage, and the load current. So all of these three parameters are very important to decide the actual current that is required by the converter to feed to the load. It is then compared with current IB2 of the converter, and thus it controls the it controls the converter current. There are two very important parameters that are related with dual active bridge converters. The first one is D1, the other one is D2. D1 and D2 are the inner and outer phase shift that are being given to the converter. So these phase shifts, they allow the power transfer in the converter. So these are the controlling parameters. Lastly, pulse generation block. This pulse generation block is also very important because this block connects the whole control part and generates the pulses. So this pulse generation block works as per the signal received from the EMS. So if you receive signal 1, the pulses are being generated. If you receive signal 0 from EMS, it will stop the pulses to the converter. This is the supervisory control, which is the EMS, which is the outer control that controls all the three converters. The output from this EMS block is converter 1, 2, and 3. The input are these parameters, which is V0 as the output voltage, IR is the load current, VSC is the supercapacitor voltage, ISC is the supercapacitor current. These are some important data that are useful in deciding all the three signals that are going to the converters. These are the simulation results. We are still working on this whole system. So we have considered a few of the load current variations. At t equals to 1.1 second, we can see that the current changes to 5.3 ampere. So now there is surplus power. So we can say that the converter 2, which is battery to supercapacitor converter, since battery has surplus power, it can charge the supercapacitor. And the load is less. It is not a high load situation. When we talk about t equals to 1.83, the I load current has increased to 7.3 ampere. The data is being shown here. So at this high current demand, when the load increases, we can see from the third graph, from the third result, that the supercapacitor to DC bus converter is given high pulses in between. From the first result, we can see that the output voltage in all these conditions is maintained to 800 volt, which is the rated voltage, and there is no sudden dip in the voltage, so it is within the required range of within the 5% of the rated voltage. At t equals to 2.62 seconds, we can see that the load current has reduced from 7.3 to 6.2, and then we can see in the third result that the pulses are also reduced, like the duration of the pulse has increased now. So these pulses, they depend on the load currents, whether to feed from the supercapacitor or not. These are the battery voltage and the current that the battery is supplying to both of the converters. Again, the results are taken at all the three conditions with high current demand and the low current demand. So at t equals to 1.1 second, we can see that the input current, the current from the battery is also going to the converter number 2. It is charging the supercapacitor now. At t equals to 2.62 second, we can see that the input current of converter 2 has reduced to 0. So the supercapacitor has stopped charging. It has to feed the load because the load has increased. These are the charging pattern of the supercapacitor. This is similar to what we have discussed in the previous slide. The supercapacitor, current charging of the supercapacitor, and the converter results are shown here on the first. The top result shows the charging of the supercapacitor within that duration. And when it has to discharge, the current is 0 in the converter number 2. These are the load current variation. These are the battery voltage and battery current as per the load current variation. So we can see that when it has to charge the supercapacitor, the current is more until close to 1.1 second. And when the load changes again, it starts feeding the whole to the load and stop the charging of the supercapacitor. This is the hardware prototype that we are developing in the laboratory in order to test our energy management system. So this is a small scale version, and we will test this at high power rating in future. As we've discussed in the DAP converter, there is a primary full bridge and there is a secondary full bridge on the secondary side. Source is also marked here. The load side is also marked. The gate drive, this is an SIC based converter system. The gate drivers are shown. The microcontroller, it actually controls all the pulses. So this is one DC to DC converter, and this is connected between the battery to the supercapacitor, which is the most important unit in the HES module. So the conclusion of the whole presentation is a coordinated energy management system is developed. Each converter is designed its specific role. The battery is the primary source. And the supercapacitor handles the transient situation, the peak power load demand. The control loop of every converter is active when the converter 1, 2, and 3, the pulses to them are high from the energy management system. And the HES architecture, it avoids multiple power conversion stages to charge the supercapacitor. Thank you. Any questions? Thank you.
Thank you, thank you.
I had one question.
Okay.
So what's the speed or time of your DC-DC converter?
The switching frequency we have considered as 50 kilohertz.
And and then second question is that how rapid are these grid changes? So how rapid this system should be?
We are designing it for, as of now, at the initial stage, I have considered one cycle, like one fundamental cycle, which is 20 millisecond. And I have to check again about the whole load variations. But as of now, we have considered one fundamental cycle for the grid variation.
Okay.
Like it has to restore in between one fundamental cycle.
Okay, good. Thank you.
Thank you.
Okay, thank you, thank you. And then we have FS and Aapo Varpola from VTT.
Thank you. So the full project title is Efficient Photonics for Sustainable Imaging and Sensing. So we started roughly a year ago, and VTT is coordinating, and then we have also University of Tampere Metaplasmonics Group in the project, and the company partners are Applied Materials, ChipZero, and Vaisala, and Schott Primoseller as in-kind partner. The total budget is a bit over 3 million euros, and we will still run for 2 years. So the idea of the project is to utilize the expertise of the partners, so materials, MEMS devices, meta optics, and integrated optical systems to develop optical gas sensing and spectral imaging technologies for various applications, so process and environmental monitoring, green energy, medical applications, and food and medication safety applications. So here are the work packages. First is design work package, so we do the material selection, design the structures and devices, and second is fabrication, which is about to start soon. So there we fabricate the components, so MEMS Fabri-Perot interferometers and meta lenses. And then third work package, we integrate them into modules and systems for applications. So there we are looking into fiber coupled tunable shortwave infrared light source, tunable long wave infrared source, optical gas sensing systems and imaging systems. And fourth, of course, management and dissemination. So Meta Optics is an emerging brand of optical science, and the idea is that using structures smaller than the wavelength of the light or infrared radiation, you can manipulate the light. So you can direct it or filter and so on. So you can replace these macroscopic conventional prisms and lenses with thin ones, as you see here. But also have new functionalities, so like directing certain colors into certain direction, for example. And in this project we are working on 3 different meta lenses, so for near infrared, short wave infrared, and for long wave infrared. So moving on to optical gas sensing applications. So in general, it's a multi-billion-dollar market, and there are many applications in industrial and environmental and condition monitoring. The idea of this project is to move into long wave infrared spectral range. So in the graph you see that the mid-wave is rather crowded, so it's difficult to distinguish different absorption peaks of gases. So it's much easier in the long wave infrared part. So the idea is to create building blocks for that spectral range. And main working horse is this MEMS-based tunable Fabri-Perot interferometer filter. And here are some examples from Vaisala how using MEMS technology allows you to reduce the size of different instruments. So specifically the technologies that we are using are non-dispersive infrared gas sensors. So the idea is that you collect volume of gas in a chamber within the gas sensor, and you direct infrared light through it, and then you choose the absorption band that the wavelength so that the gas absorbs the signal, and then using the spectral tunable filter you choose a neighboring wavelength where this absorption doesn't take place, so you get a reference signal out of that. The second method is photoacoustic spectroscopy. So the idea is that you direct light into a gas chamber where the absorption takes place, and then you create a sound signal. So the absorption creates a thermal expansion and creates a sound signal, and you detect that using a microphone. And conventionally they use like macroscopic filters to change, to measure different gases. So you would need to have large filter wheels to cover many gases. So the idea is to use MEMS filter to replace the wheel. And also in the gas sensors, we are designing metal lenses to make them more compact. Well, yeah, the key thing in the MEMS technology is using the suspended polysilicon membrane so that the optical efficiency is high. So it's a black mirror made of air and silicon, which has high reflectivity. So just some examples. So this is design of long wave infrared tunable light source. So we with ChipZero we designed the system from the reflector to the passive filter and then the tunable filter. So here the simulation results of the MEMS device and then the whole system. And this device will be fabricated in the project. So moving on to spectral imaging. So the idea is that if you take a picture, then instead of color in each pixel, you have a full spectrum, and using the spectral information, you can either have higher contrast, or then you can also do like chemical decomposition, so identify chemically different targets, or just based on the contrast at different spectra. And this is a market with size of tens of billions of dollars. So in this project, the idea is to do active hyperspectral imaging. So instead of having the complexity in the camera side, we use tunable light source to illuminate the target, and then use regular cameras to take the images. So it will reduce the system complexity a lot. And yeah, here we will also incorporate metal lenses in the system to make it more compact. And the targets are food and medication safety, and also industrial measurements. So how this is linked to ChipZero? So development of novel systems with smaller footprint, so smaller size, need of resources and cost, and then developing systems with positive handbreadth, so increasing the efficiency and capabilities of photonics. And then also material competence development for optical purposes and increasing reliability and lifetime of semiconductor components, especially in metal optics. And then of course collaboration and co-innovation. Okay, yes, to summarize, so 3 RTOs and 4 companies are merging function and form for next generation spectral imaging and sensing. And we are creating novel technologies for circular economy and resource efficient and emission free industries. And specifically the developed technologies are optical gas sensing and spectral imaging, and the components are metal lenses, tunable fiber coupled light source, and then long wave infrared ChipZero interferometers. Okay, thank you. Any questions? Okay, maybe we make the schedule in time.
Yes, thank you, thank you. Okay, still one more co-innovation project to introduce. So Vipase or is this Y-base or how to pronounce?
Both work.
This one to go.
Musta tämä oli pointeri? Vai? Eikö tuo menee tuohon suuntaan, tuo menee tuohon suuntaan ja tossa. Yep. Okay, thank you. Sami Suihkonen, senior scientist at VTT, so project manager of wide-base, wide bandgap semiconductor power electronics, a ChipZero co-innovation project as well. And now finding the right buttons here. Yep, brief introduction to wide-base. It's linked to two co-innovation, two veterinary projects. Applied Materials, ChipZero, why we are here today, and also Danfoss's fossil-free future veterinary. So we have a quite good selection of companies, partners in this project, starting from the Finnish semiconductor industry, Augmetic, Applied Materials, Complex Solutions, all have interest in getting their products, processes into power electronics semiconductor market. And then the Finnish strong power electronics industry, Danfoss, ABB, Kempower here in this project, they have all interest in how to utilize wide bandgap semiconductors for their power electronic systems. So historically we've had in Finland a bit of a gap here on then wafer level, device level, packaging level expertise, but now this is something that VTT is now moving into cover together with University of Tampere CIPFAB initiative that then focuses on packaging of power electronics devices. Unfortunately, their plans were not ready yet when we were preparing this project, but we are in close collaboration with them, planning joint work. Then on university side, we have University of Helsinki. There are decades of experience on atomic level defect analysis characterization in various semiconductor materials, including wide bandgap semiconductors. And Aalto University with long history on metal interconnect development for power electronics packaging, and Lappeenranta University, who have long expertise on reliability testing, lifetime analysis of commercial, discrete, and then power modules. So together, a consortium pretty much covers the full value chain from wafer into a actual end product of a power electronics system with the focus on wide bandgap semiconductors. We had quite a crash start for the project. We got the funding decisions 2 months after the official project start date, but now we are well on speed, and also practical work of the project has started. So why do we want to do this? As I briefly mentioned already, there's a strong interest in power electronics industry in wide bandgap semiconductors because they allow more efficient, faster, smaller semiconductor devices that translate into smaller, faster than power electronic systems. But there's a lot of reliability testing that needs to be done, a lot of understanding on how these semiconductor devices really affect the end system and system level, and also this understanding needs to be extended also into semiconductor level as well. And these are exactly the type of questions that we aim to address and search solution for in this consortium. So if you list off more than concrete goals, what we want to achieve with this project is really to generate a national expertise cluster on wide bandgap semiconductors, power devices that then benefit both the Finnish semiconductor and also the power electronics industry to understand these materials better, understand the market better, and then to network, find the right experts for the right type of research question easily within the Finnish ecosystem. Then on VTT side, our clear goal is to establish national R&D prototyping testing capabilities on semiconductor level on wide bandgap semiconductors, with initial focus on gallium nitride, moving into ultra-wide bandgaps, aluminum nitride, and a bit of a question mark with silicon carbide, since our neighbors in Sweden are already quite advanced, well, and of course our then Central European RTOs have worked quite extensively on these materials. The same, I understand the same goal is shared by Tampere University CIPFAB, where they extend this into pilot line packaging level. So in the optimal case, we would have everything from substrate into a packaged discrete in Finland in collaboration with CIPFAB. Then a strong interest from power electronics industry is on the reliability concerns testing capabilities. That's clear focus for Lappeenranta University of Technology. Then longer term research goals, questions extend into new materials, aluminum nitride, looking into gallium oxide, such materials, their potential for future semiconductors, especially then targeting for power electronics then applications. This is then more the university's focus area. And we do understand that we are, with gallium nitride, especially silicon carbide, even with aluminum nitride, there are other players globally who have done this quite extensively, longer time, so establish good links to then other research institutes in Europe, in Japan, in the US. If we take a look of the project scope, the work is in 5 work packages, interfaces and defects. The important aspect in gallium nitride silicon carbide devices, where focus is on surface passivation, gate dielectrics, with then strong focus on ALD technology and utilizing that in power devices. And the same then interface problems occur also on the substrate material interface. So looking into what happens, especially in nitride silicon substrate interface, and that's something that was mentioned earlier in ChipZero project. We have same type of problems and research questions here. Then work package 2, that's then more focused on power devices, so our then prototyping testing capabilities on wafer level, die level on wide bandgap power devices, namely gallium nitride. Third one then clearly focusing on packaging reliability, so looking into metal interconnects, then reliability testing of commercial modules, and then the emerging materials and international collaboration as a separate work packages. If we start with work page 1 and then our current progress and first results, here the focus will be on oxide or dielectric material interface for silicon carbide MOSFET, gallium nitride hemmed or mishemmed surface passivation, and then gate dielectric interface, and that's one of the main source of reliability issues if we consider this atomic level then phenomena. So this is something that we at VTT are putting then our first efforts here, working on then developing different dielectric stacks together with our consortium partners, such Applied Materials and Comtech Solutions, who has novel crystalline oxide passivation technology for these interfaces. We are starting quite from fundamentals, so utilizing the not only our VTT's micronova equipment, but VTT's characterization equipment in the Otaniemi area. So we have a state-of-the-art time-of-flight SIMS tool that allows us to analyze impurity concentrations in and alloy compositions of wide bandgap materials going into PPB level. Also plasma Fib that allows us to do device characterization, elemental analysis, even crystal analysis on semiconductor device and even module level. And VTT Micronova recently purchased a Mercury CV prober to characterize especially wideband gap semiconductor and dielectric interface defects on then a small coupon to 300 millimeter wafer scale. So we are ramping all these measurement capabilities for these material systems. If we then take a look of our work on power devices, here as mentioned, our first focus is to have a test devices prototyping capabilities of gallium nitride HEMTs in Micronova. So here we have a joint work of VTT and Aalto University, one excellent master thesis where we demonstrated gallium nitride MIS-HEMT process flow and first results of a simple straightforward GaN MIS-HEMT structure with a gate oxide under the gate controlling the conduction path. So this is something that we are, that's then our baseline process and allows us to characterize the oxides and then our process flow in a large. Going into work package 3, here main focus is in Aalto's and Lappeenranta's work. First result is a overview, a master thesis by Aalto, and very good overview of wideband gap power device packaging technologies from then metal, this interconnect into the different module size. It's a good overview and reference then piece for a persons interested in the topic. On emerging materials devices, here we have drafted first plans. Our first focus would be on aluminum nitride. We are establishing discussions with Central European research institutes on supply of aluminum nitride single crystalline substrate material, and then coordinating our research efforts with their roadmaps. So I hope to be able to share more in a year from now on this work package. And the international collaboration, that's our current list of partners mentioned in the project plan from UCSB, one of the leading research groups in gallium nitride research. University of Helsinki has several research visits planned there. We're working with on gallium nitride epitaxy, working with Lund University, gallium nitride single crystalline substrate from Unipress Poland, Fraunhofer IMWS on then characterization TM measurements of devices and discretes. VTT's first researcher visit would be the Fraunhofer IISB to study atomic layer etching of GaN epistack for a MIS-HEMT process and integration of dielectric into the etched epistack in the same vacuum chamber where they have a previous expertise on the processes. And IKZ Berlin, that they can supply us also aluminum nitride single crystalline substrate for epitesting. DTU Denmark, there's Lappeenranta University is coordinating their module testing, reliability testing development together with DTU. So that's our project and a brief intro. So as a summary, we target to advance Finland's expertise in wideband gap semiconductors, especially for power electronics, through collaboration and establish our national capabilities for prototyping, testing of these semiconductor systems and the devices. Work has started according to project plan, perhaps a bit late, and we are open to discuss any joint research ideas or research questions with the whole community here. So, yep, thank you for attention.
I have again a question. So if I understood correctly, so your intention with gallium nitride is to set up this process flow and to get on the level of making to preempt my own question, because this gallium nitride is quite advanced. It's a mainstream only on the
Yep, on test device level. We're not aiming to compete with gallium nitride HEMT manufacturers, no. But yeah, to have a baseline process flow here that would enable us to then characterize, for example, gate dielectrics in a close enough environment or with close enough test vehicle to a commercial product.
Yeah, maybe on this type of applications, maybe the latest information is not available on the scientific papers. That's my one of my messages. Then, are you focusing on component development in the future? Not necessarily in this. I mean that different kind of component architecture for gallium nitride.
Yes, that's also planned for looking into vertical devices, and then well, a big question is then how much do we want to do in-house? How much do we want to get outside, and what would be the exact focus of VTT's work? That's still being drafted. So now we have few epi suppliers for GaN epi wafers, and talking quite much with European RTOs, then what would be the VTT's role in the forthcoming larger EU consortia. But if you have any ideas, thoughts on this topic, would be very good to discuss.